So with that, we're moving into the next presentation. And again, this is kind of a follow-on to what Hugh did. One of the things we've done as part of our content is adding in a section which I call Industry Update. And Mark, coming in from IEEE, is part of that. IETF, of course, ICANN, Aaron also are part of Industry Update. But in this case, Mark is following up because what he is going to talk about, which is what's happening in the future in Ethernet with 800 gig and 1.6 tera, falls directly behind what Hugh was talking about with respect to what's going on with Ultra Ethernet. So Mark is a very good friend of mine. We worked together at Cisco for quite a while, and he is one of the chairs on the next generation Ethernet project for IEEE. He's a distinguished engineer at Cisco. I don't know why he keeps working there, but he loves it, and he comes from Ottawa, so very close by. Welcome, please, to Mark. Thanks, Mark.
Working? Can you guys hear me?
Yep.
Yeah. Okay. Good morning, everyone. Thank you for coming. I hope to be as interesting as Hugh. Hugh talked about all of the pressures that are coming at us with all the AI, the HPC, and as he so well explained, there's this reduce it down to the 4-layer network model. I'm going to talk about the lower layer, Ethernet, which is really the tail being wagged by the dog here. But our job is to try and keep up with these loads and these pressures and these applications that are coming at us. So as Steve said, I work at Cisco. I'm presenting here today wearing my IEEE hat, which is I'm the vice chair of the latest project on IEEE, working on the 800 gig and the 1.6T Ethernet. All right, so I do want to acknowledge that a lot of this, I had a lot of help with a lot of my colleagues that we worked together on this project. It's probably one of the biggest IEEE projects in history with everything going on. I'll try and explain all that. And the IEEE wants me to say that I'm not talking for the IEEE Standards Board Association. I'm just talking as myself. Okay, so I don't think we need to spend too much time about the market drivers. I think everyone here understands all that. But as a lowly hardware person, we have to build all this stuff to keep up, right? And that is the challenge, right? So the capacity is growing and we're trying to build these ASICs to keep up. And this is a large part of what, in my day job, working at Cisco, I'm working with all the teams to try and figure this all out. And the way we do it is obviously the chips are getting bigger, the SerDes are getting faster, the number of pins we put on the SerDes are getting higher. And then the data rate that we come out of the SerDes, the lane rate that we talk about is getting higher and higher. And we just keep tick-tocking through all of these things and trying to keep up with the capacity and then small little things about worrying about power and cooling and all those things. But those are the pressures that are coming at us in terms of what we need to build to keep up with everything that Hugh is explaining and the pressures of the network that's driving all of this work, right? So this is like deep down in the physics. We're pushing physics as hard as we can. Okay, so where is Ethernet? As Hugh said, Ethernet is pretty much everywhere now, whether you're talking between buildings over a WAN, RAN space, or you're talking within the data center, right down to the interconnects into the compute, as Hugh was talking about. Ethernet, everything is defined there. We spend a lot of time working, making sure we optimize for each one of these. We're under a lot of power pressure, under cost pressure, performance pressure, and so we're trying to hit that. And what's changing and what's accelerating things is exactly what he was talking about, whereas we would typically talk about a network, a front-end network. Now we have all this back-end supporting the AI and the HPC work, and that's really just accelerating, again, the pressure on the speeds and feeds and power and cost, as usual. So now let's narrowing down into what I want to talk about and give an update on. So Ethernet right now, what you can go and buy and is ubiquitously used everywhere is largely the 400 gigabit Ethernet technology and standard and all the different variants there. And that's largely based on 100 gigabit per second technology. So we call it 100 gig per lane, or you'll hear SerDes, or we just have the speed coming directly off the pin on your ASIC is at 100 gig. The speed of the optics is also at 100 gig. We do a whole bunch of tricks to achieve that. But those are maturing out right now. And so when we started the project of beyond 400 gig, what's that going to go be? everyone threw everything that they wanted in there. And there was a lot of, hey, I want to go do 100, I want to reuse my 100 gigabit per second technology, but just use 8 of them instead of 4 of them, so 8 wide. And that would drive the definition of things like the MAC and the architecture. And so that was part of the project, but then it was like, okay, we need to go to the next highest speeds and feeds, and that really shifts us up into this 200 gig per lane technology, which is really, really hard. And what we found out is this project was so big because we had all those different layers of the network that we're trying to hit copper up to the long haul stuff, or the longer distance stuff. The project got really, really large, really, really complex. And so what we ended up doing is splitting the project in half and say, let's get the 100 gig per lane stuff out of the door as quickly as possible. That allows people to have 800 gig Ethernet ports running in their network, although there's not a lot of that yet, but it defines that people know how to go do with it. It's largely based on the 400 gig Ethernet stuff, so everyone knows when we're building our chips and taping them out that we can go support all that, and that work's all done. And what's left now is the higher speeds, or the 800 and 1.6 terabit, all based on 200 gig per lane. And really, what's unique about that is obviously the 200 gig per lane technology, but it's also the first place we're defining the 1.6 terabit Ethernet MAC, right? And again, we're going to go and work through all the different PMDs, as we call them, physical media dependence, so copper and optics and so on. Okay, so one of the things that has been very ubiquitous and common for the last, 15 years is the big, from a physical layer problem perspective, the big issue is the speed step, right? So we call it the SerDes, or the lane rate, and these are the speeds that are coming off the ASICs. These are the speeds we try the optics, and those are the really big challenges for the people that dwell down in the hardware. And so once we make that step and we figured this technology out, we then use it as many different ways as we can to create all the Ethernet interfaces and all the network interfaces that we use. So when 100 gigabit Ethernet came out as an example, there was a very early version of it, which was based on 10 gig SerDes, so we had 10 by 10. And so if you look at the 10 gig on the x-axis and you go up towards and find the 100 gigabit Ethernet line, you can see 10 by 10. And so over time, as we speed up these SerDes, we're able to march down the width. And the reason you want to go down and to the right here is because it's cheaper. It's cheaper, it's lower power, but you can't do it before the technology is ready, right? So you're always trying to push down to single lane, always trying to push down to single lane because, it's maybe one fiber, it's maybe one copper cable. It's just lower cost, lower power. And so the big push is how quickly can we get this new lane rate out and allow everything to come down in cost and power, right? So with the 800 gigabit Ethernet based on 100 gig per lane, that was known as 802.3 DF. All that was what I have circled in the red line. It was just adding the 8-lane variant of the 100 gig per lane. And then with the second project, or what's left, the 802.3 DJ project, that's all based on the 200 gig lane, and that's really creating this whole family, right? And one of the things that has really changed in the networking world is before, breakout, I guess, is the easiest way to say it. So now a lot of for efficiency, cost efficiency, power efficiency, you're all dealing with a lot of networks where you have a 400 gig module, as an example, that gets broken out and you're running it as 4 individual 100 gigabit Ethernet, right? So that's breakout. And as the industry was learning how to do all this stuff, we kind of specified all these things at different times, and it was a bit of a mess. So now we're recognizing right off day one, even though we're working on 1.6T and 800 gigabit Ethernet, it's 200 gig per lane, so let's specify 200 gig Ethernet, let's specify 400 gigabit Ethernet based on those lanes at the same time. So we've got all of these variants in there as well. Okay, so where are we with this? What's the scope of the network? The key themes I kind of want to point out is this project's in flight. It's going to cover, as I said, the 200 gigabit Ethernet, 400 gig Ethernet, 800 and 1.6T. We're rolling in all the breakout at the same time. all the electrical interfaces that people would know and understand. Basically, we're trying to give the industry everything that they know how to use and know how to build their equipment around, right? So we have all the electrical interfaces. So those are copper cables, which are, everyone thinks copper cable would be dead by now, but it is even more important as we get into the AI ML world. We have all the backplanes, the chip-to-chip, the chip-to-module interfaces all being defined so we can go build all of our equipment. And then in the optics, it's very much focused on single mode. That's the primary market driver for that. So we have a lot of different reaches there, and each reach has different solutions to be able to achieve the reach in the lowest cost way of doing it. So we have very short 500 meters all the way up to 10 kilometers using, I'll probably use the word IMDD, which is intensity modulation direct detection. This is turning the laser on and off basically. But also the coherent technology that I imagine you're all familiar with, which is used for the much longer distances, the long haul, thousands of kilometers, is coming down and being relevant into these shorter distances as we get faster and faster. This IMDD technology is sort of running out of gas a little bit. Not yet, but for the longer reaches like 10 kilometers up to 40 kilometers, we now see some of the coherent technology coming in, sort of a coherent light or low power coherent coming in. And so we have to, again, bring those into the Ethernet sphere. And this will be probably one of the first times that the coherent technology will be part of the Ethernet. Okay, so a bit of an eye chart, and as I said, there's a lot of moving parts in this project. A lot of people want a lot of different things, and so the best way to describe this is if you look on the left, you've got all of the Ethernet data rates. If you look on the top, you've got all of the different PMDs, the electrical interfaces, the optical interfaces, and then it's a bit of an eye chart, but these are everything that's on this is a spec that's being written right now. Right, so we have different variants for 200 meters, for 500 meters, for 2 kilometers, 10 kilometers, 20, 40 kilometers. On the optics side, we have copper cables, we have backplanes, we have the AUI, which is the electrical interface from the chip to the module. All of those being defined, everything is a little bit different and unique, but at its main level, it's going to offer everything that we had before. Right, so if you're building out today with 100 gigabit Ethernet and your topology is a certain, in a certain state, a certain infrastructure, we're trying to make sure you reuse all of that existing cabling infrastructure that you've used before. So that's the main goal. It's an interesting question about what we do next, whether we keep doing that, but that's always the question that goes in there. And so for all the electrical work, everything's based on 200 gig per lane PAM4 signaling. On the optical work, everything in blue is, again, the 200 gig per lane PAM4 signaling. And then we have the longer reaches based on the 16 cam coherent. And so what is it going to provide from a lot of the network user point of view? It's everything that you kind of know today. You can have a switch box. It's going to have a certain port on it. We have different pluggables, the QSFP-DD, the OSFP. All of the technology we're defining is being defined so that we know it'll fit in there, we know it'll work. You'll be able to do all of your copper cables, all your single mode I talked about, some of the longer reaches as well, and everything fits. And a lot of time and work is spent into making sure that what we're defining is compatible with current CMOS technology, with the current form factors, the configs on the systems, whether we can cool this, all of this stuff that is part of the in my world where we're trying to implement that we care about, right? And so I think we're on a glide path to getting that all sorted out. So one of the other things it'll provide is compatibility, right? So one of the great value propositions around Ethernet itself is it always works. It's guaranteed to interoperate, which is a big deal. But second, it also has compatibility back with the previous generation. That's very, very valuable. And then from an implementation point of view, people can go and build multi-rate and technology and things like that. So you will be able to, with the architecture and the way things are set up, you'll be able to take a platform, say a 50 terabit platform now that's all based on native 100 gigabit per second, and you buy your new box, which is based on the new 200 gig per second native technology, doubling the capacity. There's a lot of reasons why you want to go do that from a power savings or a cost savings point of view, but they will work together with each other, right? So you will be able to go and take pluggable module, plug it into one, pluggable module, plug it into the other, as long as it's the same interface, meaning it's the same sort of 800 gig G base, DR4 or something, as long as it's a compatible Ethernet interface, it will work together, right? And there's a lot of work has gone into making sure that all works and the architecture is consistent. And so I think it's just saying the same thing. So the logic and the architecture is all being set up to make sure it's consistent, everything's compatible, as long as you have those 2 points. One of the small little details is obviously on the 800, on the sort of the 1.2T4 switch here, that would be a 1.6T pluggable module. And with the breakout and everything people are doing today, often that's a 2x800. So as long as the 800 that you have in one end and the 800 you have in the other end is compatible, everything will just work. Okay, so how do we do this? There's a lot. 200 gig is very, very hard. It's pushing right on the edge of where everything is from a physics, from an engineering design capability. So we had to kind of maintain that Ethernet architecture. We had to extend it to make sure that we could put in some extra hooks to make sure that all of this worked. Obviously, the 200 gig per lane stuff is very hard electrically, very hard optically. For 400 gig with Ethernet, there was quite ubiquitous use of forward error correction, but done in a way that was very simple for the user. It became a don't care. It was just always there. It was always the same. It was necessary. It helped us get to the 100 gig per lane. But now for the 200 gig per lane, we're having to actually add a few more complexities into there, and I want to share some of that because it is relevant to you when you're building out your networks. So the general architecture, I don't know if people care about these kind of pictures. If you open up any textbook on Ethernet, you'll see these kind of pictures. We have followed this general architecture all the way through. It's a lot more complex with added FECs and extender layers and things like that. And I'm not going to get into that here, but we're consistent with the general architecture. Nothing's fundamentally changed. The 200 gig per lane technology is the big step. And so what are the key elements? The first one I've already mentioned. Everything's compatible with the current technologies, whether it's the optical EML, silicon photonics technology, the cable manufacturing, the fiber itself, all the CMOS. We make sure that we're all compatible with that. Again, we're trying to reuse as much as possible, so we just define something once and then we figure out how to use multiple lanes of it. That again keeps the cost down, allows the integration to happen, which brings the power down. We've had to add a whole family of forward error corrections. Different reaches have different forward error corrections, but again, done in a way that it doesn't break the architecture at all. So from a switch platform point of view, you can be a bit a bit transparent to all of this, but it is happening under the hood, and it does have impact and effect. So I'll talk a little bit about that. And then because the 200 gig is so right now very challenging, we're adding a whole bunch of extra optional features like link training or link negotiation that'll help when you plug it in, bring it all up, make sure all the settings are set. Now, this is kind of known in the copper cable environment and may be happening behind the scenes and you're not aware about it, but now we're moving it into the optical domain as well, and that hopefully will make things a little bit easier. So I've talked about this a couple times. I just want to go into it. So when we talk about the multiple effects schemes, this is how I kind of break it out. So you would have all the components which are sitting inside your equipment. You have your ASIC with your Mac. You may have, you'll have traces across the board. You may have an IC on the board, which is a retimer, repeater, to get the electrical signal to the pluggable module. Then you go to some outside plant, and then you hit your equipment on the other end. And anywhere in there, errors can happen. And there's a whole bunch of 200 gig. There's a lot of things that can go on to add errors into your solution. So how do we fix that? The first step is just to put forward error correction. And this allows the ASIC on either end to correct the errors, allows us to run the link in an errored state, which is a much cheaper and lower power way of doing it. But it corrects all the errors. And this kind of end-to-end FAC is what is ubiquitous in the 400 gigabit Ethernet. So you may or may not be aware this is happening, but it's there in your 400 gig links. it's all there. You got end-to-end, it's in all the ASICs. And it does add some nice capabilities because you can now dig in and you can go look at some of the effect statistics. Now, actually, you can learn a lot, right? When something's going a little bit wrong, you can have a look at what your prefect bit error rate is, and if there's burst errors, you can detect them by looking at what your T counts are and through that. So we have this 400 gig, we have this end-to-end FEC built in, and this is what's used for all of the copper cable reaches. This is what's used for all the optical reaches up to 500 meters. So once you go above 500 meters, it starts getting a little bit harder. And so what we've done is we've added something which we call a concatenated FEC. And what this means is you then have your end-to-end FEC that's sitting there, and then, but as the signal moves into the optical module itself, it then gets an extra FEC on top of that. And then what that means, you encode a second error correcting code on top of that. And so the disadvantage with this is you have to go a little bit faster because every time you encode, you're adding more data rate. So that pushes things up a little bit, but the error correction capabilities on the receive can mitigate a lot of the impairments that are now happening because you're trying to go further, right? And so you get this concatenated FEC, and this is used for like the 2 kilometer and the 10 kilometer. It can add a little bit of speed, it can add a little bit of latency, but nevertheless, this is how you would go use it. And so we're using this on the IMDD links up to 10 kilometers, and we're using it actually in one of the coherent links, the 10 kilometer one. And then when you really want to go far, you want to go sort of 20 kilometers, 40 kilometers, we're very much leveraging the FEC technology that's been used in sort of the longer haul, the ZR, the 80, 100 kilometer, 500 kilometer, 1,000 kilometer technology. That's a FEC that's called OFEC. And we just set it up so that the end-to-end FEC is operating. It just gets terminated in the module. So you can get a pluggable 800 CR module, plug it in, it'll terminate that end-to-end FEC in the module. It'll use its own OFEC, send it out, and then decode, re-encode on the other end of the link. Right, so all of these things are kind of new for Ethernet with the 800 gig per lane tech, sort of the 200 gig per lane technology, and so the 800 gig E 1.60. Again, it'll be the same usage model. It's just there's a few more things going on under the hood, and again allows you to go in and explore and get some of the statistics, which is helpful. Right, so this 200 gig really is hard, right? It's come right at the, and this is always the trade. We thought 50 gig was hard, we thought 100 gig is hard. We know 200 gig is hard, but it's you know, so what have we had to do, right? We've talked about a lot of this. We're finding margin everywhere. We're trying to tighten things up. We're trying to look at the packaging of the ASICs. We're trying to remove packaging where we don't need it, or define it. You have to have better packaging. We're looking actually into the optical fiber itself and saying actually the way it's been specified is we haven't really worried about some of the specs, right? So they're very loosey-goosey specs. They're a bit kind of rough. And so we've gone in and looked at it and done a lot of study about things like dispersion on the fiber. So even though the fiber the fiber specs haven't changed for decades, and they haven't had to change for decades because everything just works, we're now pushing into the speeds where some of this dispersion is becoming a problem. And we've done a lot of studies to actually find out that you can guarantee just buy the same fiber you've been buying before, but now we know that, and we have much better studies on the fibers, that everything will just work. But we had to go do that work, because if we just use kind of the worst case specs that have been around for decades, it was right on the hairy edge. So there's a lot of, you know, again, this is all kind of below the scenes, but everything that was, we're just needing to tweak, find crumbs everywhere we can to make this work. And we know that over time, everything's going to get better. Technology matures, we get margin. So in 5 years' time, we'll consider this stuff trivial to go do. But right now, it's challenging. But you know, I was at a conference, when was that? About a month ago in Europe. A lot of this is being demonstrated already. Right? So the technology's out there, they're seeing some very good margin. We just now have to make sure it's all interoperable. So what are we doing, just to kind of summarize, to make this easy or easier, right? Everything I've talked about before. We've got the inside, the equipment, the outside. We've got this end-to-end FEC that we go use. That's very helpful. We then have the ability to put a concatenated FEC or a segmented FEC over the links that we need to go use it on. We have the ability to do auto negotiation between the two endpoints. This is typically a copper cable. Negotiations is setting all the equalizer settings, making sure that everything works out right, because when you plug it into one port to another, you may be on a short trace on one of the pieces of equipment and a long trace on the other. You have to adjust everything. So we want to negotiate all that. And then we're now adding in, I guess this is on the negotiation piece, we're adding in the link training. So each hop on the physical layer will now negotiate with its partner and adjust all those equalizer settings. And again, with the optics, this is new to do this. And so we're kind of inventing as we go on this stuff. And it's very, I think it's going to be very helpful to make this stuff work. Okay, so where is it? When will it be done? Standards are not the fastest process in the world. The 3DF, what I talked about, which is the 800 gigabit Ethernet, based on 100 gig, that's all done, that's published, that's out there. And with the 3DJ, we split off that project beginning of 23. And that's been moving along at a good pace. We got to the point now where everything is adopted. We've got baselines. We're deep into what we call task force review. This means we're just getting rid of all the remaining TBDs where there's a little technical detail that we don't know, and we're refining and refining. And the thing that IEEE does very well is they have a very, very thorough and deep review process, which takes time. But it's because of this that the technology always works. You can move things much quicker. They tend to be done with a lot less detail, and then you end up with issues. And as Hugh was explaining, right, when you're talking about 200,000 links in a network, you can't afford to have anything that's a bit risky from a technical point of view. So we're looking and projecting that this project is going to be published in around mid-2026, but rather than everyone just thinks you're not going to see any product before that. What happens, and what has always happened in the industry, is when the technology reaches that kind of mature level, which I would say it's at now, we've got a few TBDs left, it gives people the confidence to start taping out, start making protos, putting them out there. And as I said, on the optics end, there's already a lot of demos out there. So this, I think, is going to be a very sought after and adopted piece of technology, driven a lot by what Hugh was explaining and all the AI ML work that's coming at us. And so there's a lot of pressure to get this out as quickly as possible. Okay, so in summary, we're anticipating this all to be published middle of 26. This is like the foundational work that the industry does in terms of moving the lane rates up from 50 to 100 to 200. This is where the work happens. It's hard, it's very thorough. We got a lot of people focused in on it to guarantee interop and backwards compatibility. And there's a massive sort of broad industry cooperation, collaboration going on amongst all these physical layer experts. And so I will be in a room as big as this, working on this sort of 6 times a year, trying to get everyone to converge down. So it's a huge amount of effort, because these are the big steps. And now once we've got the foundational piece in place, then what happens, right? Once you have that there, you can look at some of the new things, like Ultra Ethernet Consortium, like the Ultra Accelerator Link Consortium that's going to be building upon these. We've got the whole space around the linear optics that you may have heard about. Again, that's building on these specs that we're writing there. And so with that, I'll say thank you very much for your time. And if anyone has any questions, I'm happy to take them.
Mike?
That's fine. I'll speak loud.
You're good.
Hey, I'm Xavier Clark with Harris Computer. You mentioned that right now you guys are kind of on the edge. You're picking up little crumbs here and there of what's physically possible. Do you see us needing to move to different standards, only optical, things like that? Or do you think that just as technology gets better and better, and as we maybe get smaller processes, stuff like that, 1 nanometer becomes more popular, that we can continue in the same size form factor right now?
I have every confidence we'll figure out the next one as well, right? We just have to, because we can't build the equipment without solving these problems. It gets harder and harder. I'm actually, I have to fly out tonight and talk at another conference tomorrow, which is sort of the beginning of what's next, right? How do we sell 400 gig per lane and stuff like that? So that it feels, every time this happens, I've been around this a long time, every time this happens, we think, okay, we're done. I don't see how we're going to go any faster. And then, you know, there's a lot of creative people. You get people in a room together, a lot of commercial competition, and we just figure it out. So there's already stuff brewing. I completely anticipate we'll be getting to the next generation and probably starting it. It takes a long time to get the projects done, so starting it will probably happen in, I don't know, sometime in the next year maybe.
Cool. Thank you.
Okay. Anybody, anything online? Okay. Any other questions in the room? Then please give a warm thank you for Mark.
Okay, thank you for your time.
Appreciate it.